and welcome to another WJEC A level physics question. This time it's question 4 from June 2004's PH1, and it's a question about measuring the Young modulus of a metal in the form of a wire. Now the question gives us some information extracted from a textbook for a sort of fairly standard way of measuring the Young modulus. What we've got is a pair of wires. We have a weighted reference wire and a specimen wire, and if I scroll down a little bit on there, you'll see on the diagram that there's a vernier mechanism here, a vernier scale, a bit like the vernier calipers you may have come across in lessons, that's used to measure the extension of the specimen wire compared to the weighted reference wire. You may have come across a similar method using something called Searle's apparatus here. So basically both of these wires, same material, same length, are attached to the same support. Here the ceiling, both wires have weights added to them, first of all to make sure that they're straight and kink free, and then the left hand wire here has different loads added to it to make it stretch, and its extension is measured compared to the reference wire on the right hand side there. Also during the experiment you'll find that you will measure the diameter of the specimen wire in lots of different places. Ideally measure the diameter twice in every position, rotating your calipers or whatever else you're using, maybe micrometers, through 90 degrees just to sort of check the uniformity of the diameter and to check that it's sort of not squashed in any places, so it's no longer circular in cross section. First of all, we're asked to explain why a long wire is used rather than a short wire, and basically the idea is if you have a long wire you're going to get a greater extension. So let's put that down to start with. So I'm writing wife instead of wire. So we've got a longer wire to give a greater extension. Now the point of that is that when we measure that extension we'll get a smaller percentage uncertainty than if we're measuring a very small extension from a short wire. And we're always in experiments trying to limit uncertainties. Next we're asked, why is it important that both the specimen and reference wires are made from the same material? Well, one of the factors that can affect how much the wire stretches is the temperature. So if for some reason it warms up while the experiment is carried on, both wires will be affected in the same way by temperature. So both wires are affected exactly the same way by temperature changes. Next we're asked to give 2 experimental precautions that have been carried out in order to minimize uncertainties when taking measurements. We can take this directly from the text. We could go for something like multiple readings of the diameter taken. The idea of that is that the mean is more likely to be a good representation of the actual diameter than any individual reading. We could go for the fact that readings are repeated, ideally when unloading. So what happens with certain materials, rubber for example, is that it doesn't stretch in exactly the same way as it unstretches, if you like, when we remove the load there. So we always, if we can, with stretching experiments, take repeat readings, putting weights on and taking weights back off afterwards. Next we've got to state what's meant by the elastic limits. So this is the load up to which the material will return to shape or return to its original length. And what we would ideally do at the end of the experiment is remove all the weights from the test wire and see if it's back to its original length, so that we can sort of guarantee it's not exceeded this elastic limit. For the next part of the question, we've got a graph of load against extension for the specimen wire. We're given that the original length of the wire was 1.8 meters and that its diameter was 0.32 millimeters. Then we've got the graph, and we're asked to use the graph and the data to first of all determine the cross-sectional area of the specimen. Well, cross-sectional area is pi r squared because these wires are circular in cross-section, So it's pi times, now the diameter was 0.32 millimeters. We've got to make sure we use the radius of 0.16 millimeters. And we've got to remember it's millimeters, so we have to turn it into meters. If we stick those values into the calculator, we find ourselves getting an answer of 8.0 times 10 to the minus 8 meters squared. Then we've got to find the Young modulus of the specimen of the material. So what we've got here is we can use the Young modulus formula, E equals FL over A delta L. If we rearrange that into the form where we've got F equals something, we'll have F equals EA delta L over L. And if we compare that to Y equals MX plus C, you can see that if we've got force on the y-axis and extension on the x-axis, then the gradient is EA over L, and therefore E is the gradient times L over A. Now we could, if we wanted to, just put values from the graph directly into this formula, but if we did that, it's not generally as good an experimental method as using the gradient, because a gradient takes an average of the results. Now in this case, this gradient is basically a perfect straight line, so it wouldn't matter what values we chose. But scientifically, always try to use a gradient. So I just made a slight mistake there. Always use the gradient rather than any individual value. To find the gradient, is the change in y, 20 over the change in x, which is 5 times 10 to the minus 3, times the length of 1.8 meters, divided by that area of 8.0 times 10 to the minus 8. And if we put those into a calculator, we come up with an answer of 89.5 gigapascals. And that's a reasonable number for a metal. The Young modulus of a metal is typically sort of 100, 200, 300 maybe gigapascals. So not a bad answer. So thank you very much for listening. Please remember to like and subscribe. Goodbye.